Welcome everyone. This video is CCBYNC. All right, we are to the final bit here. We are going to do de Moivre's theorem. I'm sure I'm mispronouncing that name. That's named after a person, obviously. And basically, if we have our polar coordinate written in polar form, or complex number, pardon me, written in polar form or trigonometric form, those will go interchangeable. Then if we want to raise it to a power, we say that z to the n power is r to the n power times cosine of n theta plus I sine of n theta. This is very easy to derive from the multiplication derivation. So you can see we're adding them up n times. And we're just going to jump right into this. Now, the reason that we would do this is raising in standard form to a power can become very complicated, especially if it's a really big power, because then you have to FOIL and FOIL and FOIL over and over again. This way, we just convert it to polar form, and you can see that the formula is very, very simple to use. So we'll take our first example here, and we have our complex number. Here's our z, and it is raised to the third power. So very nicely, very quickly, our z to the third power becomes 4 to the third power times the cosine of 85 degrees times 3 plus I sine of 85 degrees times 3. And that gives us 85 times 3. 255 degrees. 4 to the third power is 64. Cosine of 255 degrees plus I sine of 255 degrees. And they ask us to put it into standard form. So I'm going to distribute the 64 and do cosine of 255 degrees. Now I need to make sure that I am in degree mode before I do this, which I am. So this becomes 64 times cosine of 255 degrees. You can see that's negative 16, and I believe it says to round it to 2 decimal places. It does. So 16.56 plus 64 times the sine of 255, negative 61.82 I. Let's rewrite that. Negative 16.56 minus 61.82 I. There we have it. Not too bad. Now, the tricky part is when we're given in standard form, like we are for this next example here. And we have to first convert the complex number into polar form, and then we can raise it to the 5th power. So let's start with A, and let's change colors here. So A, we have z, in this case, is negative 2 root 3 minus 2 I. And first, we're going to convert this into polar. So r is equal to the square root of, and by the way, please note I am in quadrant 3. So quadrant 3 in this case, because both a and b are negative. So we're going to get the square root of negative 2 root 3 plus negative 2 squared. And this becomes the square root of 2 squared is 4. 4 times 3 is 12. And we have negative 2 squared, which is 4. This gives us root 16, or 4. So r is 4. And the tangent of theta is y over x. That's negative 2 over negative 2 root 3. or a positive 1 over root 3. Now we got to be careful. This is going to give us the angle in quadrant 1. And what we'll have to do is add pi to that to get it in angle in quadrant 3. So this very nicely is on my unit circle. And so I can see that the tangent is root 3 over 3 at pi over 6, but I need the version over here in quadrant 3. So here I am at 7 pi over 6. So that is my angle. So theta is 7 pi over 6. What this means is negative 2 root 3 minus 2I is 4 cosine of 7 pi over 6 plus I sine 7 pi over 6. Now that we have it in polar form, now we can do z to the, well, that's going to be 4 to the 5th power times cosine of 5 times 7 pi over 6 plus I sine of 5 times 7 pi over 6. And let's see what we get. It looks like we're going to get, see, 4 to the 5th, that's going to be a big number. Let's see, 4 raised to the 5th power, 1024. And this gives us cosine of 35 pi over 6 plus I sine of 35 pi over 6. Now I need to be in radian mode for this one. So every time you should be checking, because I got my angle in radians. By the way, you could do this whole thing in degrees, just make sure you're in degree mode the whole time. And they say that they want this answer in standard form. Let me show you what that looks like. That's the a plus bi. A plus bi. And so I'm going to actually do, again, I'm in radian mode. So 1024 times the cosine of 35 pi. Actually, we're not going to do this. We're going to drop this down and subtract 2 pi from that several times over. So let's do that. That's going to be much better. 35 divided by 6 minus 2. Still not, minus 2. Here we go. So that's the same as 1024 times the cosine of 11 pi over 6. Plus I sine of 11 pi over 6. And now we can get our exact values with this. I know it says round your answer to 2 decimal places. We'll have to do that for B. For this one, we don't have to. We can actually get exact answers. So let's see, 11 pi over 6. Let's get our unit circle out. Cosine of 11 pi over 6. Here's 11 pi over 6 over here. Cosine is the x, so root 3 over 2. The sine of 11 pi over 6 is the y coordinate, that's negative 1/2. And 1024 divided by 2 is 512. So this becomes 512 root 3 minus 512 I. So there is our answer. And let's separate that out real quick. Utilize my space a little better for part B. Part B. So I'm going to say that z is negative 1 minus 4i. Once again, we're in quadrant 3 here. And this one's going to get messy. I'm going to use the memories in my calculator here. So let's convert this first. Let's get r. R is the square root of -1 squared plus -4 squared. So there's root 17. And I'm going to rewrite root 17 as 17 to the 1/2 power. Next up, tangent of theta. Again, keeping in mind that we are in quadrant 3 again. I know that because both A and B are negative, so I'm in the third quadrant. Tangent of theta is -4 over -1, or just 4. Now, once again, when I do inverse tangent, this is going to give me the value in quadrant 1. So I'm going to have to add pi to that. So once again, make sure I'm in radian mode, which I am. And now I'm going to do inverse tangent of 4. Now this is going to be quadrant 1. We can see that. It's between 0 and pi over 2. I need quadrant 3. So I'm going to add pi to that. So the theta of interest, I'll say 4.467. And I'm going to store that, remind you how to do that. I'm going to store that into memory A. So I'll put that into memory A. That way I get to preserve all those digits. So we now have that -1 minus 4i is root 17. I'll show you why I did the 1/2 here in just a second. Cosine, I'll say 4.5 plus I sine 4.5. All right, so what does that mean for us? We now need to do z to the 6th power. So this becomes, now this is going to be, so root 17, like I said, is 17 to the 1/2 power. So this is going to be 17 to the 1/2 power raised to the 6th power. And I wrote it that way so we could see that's just going to become 17 cubed. Times cosine of 6 times the 4.5. I, of course, will use my memory for that one. Plus I sine 6 times 4.5. All right. Now they want this in standard form. So you can see when you multiply these exponents here, you get to the 3rd power. So 17 raised to the 3rd power times cosine of 6 times memory A. Ooh, we got nice pretty whole numbers here, -495. Let's do the sine. So 17 raised to the 3rd power times the sine of 6 times A. Hey, look at that. Plus 888 I. All right. We are on to, so far what we've been able to do with complex numbers is adding and subtracting is very trivial. We can keep all that in standard form. But multiplying and dividing, we had our rules from the last lesson, from part 1. And now we can raise complex numbers to a power efficiently and effectively when they're in polar form. And now we're going to say, how do we take the square root? Or not just square root, but any root. All right, nth root theorem. Now, there's two forms of this. One of them is in degrees, one of them is in radians. I'm going to write the one in radians out. That's the one that I normally teach with, but I will do an example in both radians and degrees in case your teacher prefers one over the other. And you, of course, should do whichever one your teacher wants you to do. So we're going to let W be a given complex number, and n is bigger than or equal to 2. Any complex number Z that satisfies the equation Z to the nth power equals W is called the complex nth root of W. Now, when we have Z squared equals W, these are called the complex square roots. And of course, when it's cubed, it's the cube roots of W. We're going to let W be a number, and n is going to be bigger than or larger than 2 is an integer. So if we have this, and what we say is Z sub k is the nth root of R times the cosine of theta plus 2 pi k over n plus I sine. And by the way, I mentioned degrees. You can see I have the 2 pi in there. When we do the degrees, that's just 360 degrees. So it's the exact same formula. We just use degrees instead of radians. Theta plus 2 pi k over n. This is where k up to n minus 1. All right, let's get started. All right, find all square roots to the number -4 plus 2i. Now I want to point out -4 plus 2i is in quadrant 2, right? We go back 4 and up 2. All right, first off, because it's square roots, n in this case is 2. And I'm going to do this one in degrees for us. First thing I need to do is convert this into polar form. So we know that R is going to be the square root of -4 squared plus 2 squared. That is root 20. Tangent of theta. Now, again, we want to be careful. We are going to be in, when we do this, we're going to get, it's going to be y over x or b over a, which is going to be the 2 over -4, which is a -1/2. Now, when I do inverse tangent here, what's going to happen, and I'm going to make sure I'm in radian mode here. Radian mode, because the next example we're going to do in degree mode. It's important to remember that when we do inverse tangent of a negative, it's going to give it to us in quadrant 4, and we need it in quadrant 2. Let's again be clear. We are in quadrant 2 here. So when I get it in quadrant 4, it'll be a negative angle. I will just add pi to that, and that will give me the proper angle. So inverse tangent of -1/2 is here. You'll notice it's a negative angle, quadrant 4. So I'm going to add pi to that. Oop, I had the wrong value. Let's do that again. Inverse tangent, -1/2 plus, I hit alpha instead of, there we go, plus pi. There we go. So I'm going to take this number here, and I'm going to store that, store into A. So I have that theta is now I'm going to put 2.68. So we now have that our number, -4 plus 2i, is equal to root 20 cosine 2.68 plus I sine 2.68. And now we are going to take the kth root. I'm going to start with k equals 1. Now you'll note up here, k starts at 0. So I'm going to start k equals 0. 0, and we go up to n minus 1. So n in this case is 2. So we're only going to have 0 and 1. So we're going to have 2 square roots, and rightly so. So let's start here. K equals 0. So I'm going to plug it into here. So we have the square root of the square root of 20. I'll come back to that. The cosine of theta, 2.68. Of course, I start this off in A. I will use my memory A, that way I get all the digits. 2.68 plus 2 pi times 0 all over n, which is 2 in this case. 2 in this case. Whew. So this becomes, the square root of square root becomes 20 to the 1/4 power. This just becomes, because that's 0, that's gone. So this is just A divided by 2. And I'm going to store that as B. So about 1 point cosine of 1.34 radians plus I sine of the same value, 1.34. And again, I stored this off in B. I'm not going to write it in there, it gets too cluttered. So this is the polar version of this. So that's for both the polar and the standard form. So this is the answer in one form. I'm going to convert this now into standard form. So I'm going to go 20 raised to the 1/4 power times the cosine of B. There we have it. This is 0.49, we'll say. And then I go 20 raised to the 1/4 power times the sine of B. And that is a positive 2.06i. So here it is in standard form. Now that's k equals 0. We are now going to do k equals 1. So we still have 20 to the 1/4 power of the cosine of 2.68 plus 2 pi times 1 over 2 plus I sine 2.68 plus 2 pi times 1 over 2. And let's see what that messy thing is. So I'm going to take A plus 2 pi plus 2 pi equals divided by 2. All right, I'm going to store that as C. So this becomes 20 to the 1/4 cosine of 4.48, which again, I just stored that huge number off into memory C, plus I sine 4.48. So this is the answer in polar form. Now we'll get it in, that's 20. Now we'll get it in standard form. So I'm going to go 20 raised to the 1/4 power times the cosine of C. And this is going to give me negative 0.49. You'll see a similarity. And now 20 raised to the 1/4 power times the sine of C, minus 2.06i. And you can certainly compare these two answers that we got. There's definitely a comparison there. One with the negatives, one with the positives. All right, we're going to do another square root, but this one is going, I'm going to use the degree formula for us. All right, so here's our complex number that we want to take the two square roots of. And it actually is the solution to an equation like this. So how do we solve that? So let's convert first. So R is square root of negative 2 squared plus negative 2 root 3 squared. And that gives us 4, actually. Gives us root 16, which is 4, which is going to work out very nicely for us. That becomes 12, that becomes 4. 4 plus 12 is 16, which 16 is 4. So there's R. I want to point out once again that we are in quadrant 3 in this case. Both are negative, so that's negative, negative. So now, when I take the tangent of theta, it's going to be negative 2 root 3 over negative 2, or just root 3. Note this is going to give me an angle in quadrant 1. I need the angle in quadrant 3. So let's see where we get root 3 for tangent. That is at, and we're going to use degrees here, 240 degrees. So theta in this case, 240 degrees. Cool. So this means negative 2 minus 2 root I is now 4 cosine 240 degrees plus I sine 240 degrees. All right, so once again, K is going to start out as K equals 0. So let's block this off a little. K equals 0. And I'm now going to do the square root of R. So this becomes 2, square root of 4 is 2, cosine of 240 degrees plus 360 degrees times 0 over 2 plus I sine 240 degrees plus 360 degrees times 0 over 2. And that very nicely becomes, that goes away. So that becomes 2 cosine half of 240 is 120 plus I sine of 120 degrees. That's the polar form. They do not ask for that. So we're going to go back into standard form. And cosine of 120 degrees, 120 degrees is right here. Cosine is the x coordinate, that's -1/2. 2 times -1/2 plus I times the sine of 120, that's the y coordinate, √3/2. That equals -1 plus √3i. So there's my first answer. Now when k equals 1, we have 2 cosine of 240 degrees plus 360 degrees times 1 over 2 plus I sine 240 degrees plus 360 degrees times 1 over 2. Let's see what that becomes, that angle. So 240 plus 360 divided by 2. 300 degrees, very nice. Also within our unit circle, so 2 cosine of 300 degrees plus I sine 300 degrees is there. And now what I can do is come up with, that is, here's 300 degrees. Cosine is the +1/2. So this is 2 times +1/2 plus I times, now sine of 300 degrees is the y coordinate, -√3/2. And multiplying through by 2, we get 1 minus √3i. And you can see the similarity between these two answers. Definitely a connection. All right, we are to the last problem, and we're going to do a cube root. So I'm going to set up the whole page for this one. So we'll be able to stretch out a little bit better. All right, so we want to find all complex cube roots of -1 plus 3i. Let's start here. Start with r, converting it. R is going to be the square root of -1 squared plus 3 squared So there we go. Keeping in mind that root 10 is 10 to the 1/2 power. Now you'll note that I'm in quadrant 2 in this case, back 1 up 3. So when I do this inverse tangent of 3 over -1, which is -3, it's going to give me a negative angle in quadrant 4. And I'm going to have to add pi to that to get me to quadrant 2. So I'm going to do this one in radians. You're welcome to redo this one later on your own in degrees if you'd like, but I'm going to switch back to radians. Oh, I didn't have to switch because it was the unit circle from before. So we're in radians. But it's always good to double check every time. So here we go. Inverse tangent of -3. All right, now you'll notice that's a negative angle in quadrant 4. So to get into quadrant 2, I'm going to add pi. There it is. I'm going to store that as a. So theta in this case, 1.89, we'll say, and again, I stored that into memory A. So we now have that -1 plus 3i is root 10 cosine of 1.89 plus I sine of 1.89. And keeping in mind, n now is 3. It's no longer 2. So let's get started on this. So k is now going to go from 0, 1, and 2, right? It goes to n minus 1. So there's going to be 3 answers in this case. We'll start with k equals 0. Now, I want to also make it clear that root 10 is going to be raised, is going to have the cubed root taken to it. So 10 to the 1/2 raised to the 1/3 is 10 to the 1/6. So that's going to be my r for all 3 of my answers here. 10 to the 6th, 1/6. This is now cosine of my angle, 1.89 plus 2 pi times 0 over now 3. Plus 2 pi times 0 over 3. Because it's 0, I can just deal with that. So this becomes 10 to the 1/6 cosine. Let's see. I'm going to take that and divide by 3. Store that into B. Store it into B. Plus I sine 0.63. So now to convert it back into standard form, which they asked us to do, I'm going to do 10 raised to the 1/6 power times, actually double check again, radian mode, times the cosine. So I'm going to take the previous answer times the cosine of B. There we go. Uh, 1.185, we'll say. Oh, it says around 2 decimal places. That's okay. Next, I'm going to do 10 raised to the 1/6 power times the sine of B. Uh, 0.866, we'll say I. And it says round to 2 decimal places, so I could round this off even further. So 1.19 plus 0.87 I. There's my first answer. Second answer, k equals 1. So we 10 to the 1/6 cosine 1.89 plus 2 pi times 1 over 3 plus I sine 1.89 plus 2 pi times 1 over 3. So let's see what that's going to be. So I'm going to take A plus 2 pi divided by 3. I'm going to store that C. Let's see, 2.73 rounded off, plus I sine 2.73. And going back to standard form, I'm going to do 10 raised to the 1/6 power times cosine of C negative 1.34, run it off 2 decimal places like they say. And now 10 raised to the 1/6 power times sine of c. That's 0.59i. Here's our second answer. Our third answer is when k is now 2. Scooch that up a bit. Well, this is going to be 10 to the 1/6 times cosine of 1.89 plus 2 pi times 2 all over 3 plus I sine 1.89 plus 2 pi times 2 over 3. And let's clean that up a little bit. So I'm going to go A, that's 4 pi there, right? So A plus 4 pi divided by 3. I'm going to store that as D. So this becomes 10 to the 1/6 cosine of 4.82, we'll say, plus I sine 4.82, and that's in D now. And back into standard form. 10 raised to the 1/6 power times cosine of D. And that gives me 0.16. And 10 raised to the 1/6 power times the sine of D. So minus 1.46i. There it is. See how much of this I get in all one shot. There it is. Okay. I know that seems long and tedious and quite rigorous, but it's not too bad. Just got to be really careful and try using your memories. Thanks, everybody.